Polynomial functions. Our objectives: identify power functions, describe end behavior of power functions given its equation or graph, identify polynomial functions, identify the degree and leading coefficient of polynomial functions, describe the end behavior of a polynomial function, identify the number of turning points and intercepts of a polynomial function from its degree. Determine x and y intercepts of a polynomial function given its equation in factored form. A leading term is the term containing the variable with the highest degree. A leading coefficient is the coefficient of the leading term. And that is if you have your polynomial in descending order with the highest power first. The degree of the polynomial is the highest power of the variable that occurs in the polynomial. Let's look at the graphs of basic power functions. If I have a positive first degree function, y equals x, then it's going to look something like this. So it's positive. You can see that it is increasing as we read left to right. And first degree, there are no bends, no turns to it. How about a positive second degree polynomial? The simplest one that comes to mind is y equals x squared. That's going to be a polynomial like this. Now a positive third degree is going to look like this. A fourth degree looks a lot like the second degree, steeper on the sides and a little more flattened out at the bottom part right there. A fifth degree is going to look a lot like the third degree, but it's steeper and a little more flattened out as you get to that inflection point there in the middle. Now if we change this, we'll have something that's going down like this to be a negative function, but it looks the same as that first degree function. A negative second degree, it looks the same as the positive second degree, but it's flipped over upside down. And then you can see a negative third degree, y equals negative x cubed will look like this. Again, we have something like that. And fifth degree, something like this. So you can see here that we have similar types of behavior going on with linear, cubic, and fifth degree. They start on one side, positive or negative, and end on the other side, negative or positive. So here we're starting negative and we go to positive, negative and go to positive, negative and go to positive. And on the negative odd degrees, we start positive and end negative, start positive and end negative, start positive and end negative. But for the even degrees, if it's even and positive, we'll start up and end up as well. Even and positive, start up and end up. For negative and even, it's start down and end down. Start down and end down. So really, when we look at the degree and whether the leading coefficient is positive or negative, it's going to determine the end behavior on these. So it boils down that the end behavior of a power function is determined by positive or negative sign and odd or even power. Anything that is a positive odd power will have this type of behavior. Anything that's positive and even will have this type of behavior. Anything that is negative and odd, this type of behavior, and negative and even, this type of behavior. Now it turns out that when we look at the end behavior of polynomials, the end behavior is determined the exact same way. We're looking at just the leading term. That determines the end behavior. This is a positive and odd. So a positive and odd is going to be something like this. When we have all these other terms, means we're going to maybe have some other twists and turns along the way, but when we're talking about the end behavior, we're starting down and ending up. The way that we write that formally is as x approaches negative infinity, y approaches negative infinity. And as x approaches positive infinity, y approaches positive infinity. For the next function, we have to be careful to be looking at the leading term as being the term that has the highest power. So we're looking at negative 5x to the fourth. We have a negative coefficient and an even power. So the end behavior is going to be something like this. With this polynomial, we could have several different kinds of loops going on in here, ups and downs, but I do know that the end behavior is that it starts down and ends down. More formally, we would write this as x approaches negative infinity, y approaches negative infinity, and as x approaches positive infinity, y approaches negative infinity. Now let's look at the behavior of a graph near zeros. Just a simple power function will suffice in exploring this. If my 0 is at 0 for the function y equals x, then the behavior is that we go straight through, right through that 0. If I had something like y equals x squared, what happens is we come down to that 0 and touch it and then bounce off. If we had multiplicity 3, again, y equals x cubed, the behavior is that it comes from one side and touches that and then goes through. If I have y equals x to the fourth, here's your 0, and there we are. Y equals x to the fifth, coming down from one side and flipping through. So it looks like if we have an odd multiplicity for a 0, that it's going to go through the 0. If it's an even multiplicity, like these, that it will touch that 0, but then bounce off in the same side of the x-axis that it came from. More formally stated here, multiplicity and the graph. A graph crosses the x-axis at a 0 of odd multiplicity. For even multiplicity, it only touches the x-axis. Now we know that we have instances where our graph will turn, so we have a note here. A polynomial of degree n will have at most n x-intercepts and n minus 1 turning points. Let's look at graphing the polynomial y equals a negative 1/2 times x minus 1 quantity squared times x plus 3. Now if I were to multiply this polynomial out and get this in expanded form, I would have a first term of negative 1/2 times x squared times x for my first term. So it'd be a negative 1/2 x cubed and some other terms. If I'm looking at my zeros, my x-intercepts, I have a 0 of 1 And it has a multiplicity of 2, which means we're going to bounce off of it. So that I remember to do that once I get there, I like to put kind of a dashed halo around my 1. And then at -3, I have another 0. The end behavior, I have a negative and odd as my leading term. So a negative and odd would mean it starts up here and ends down here. One more piece would be to get the y-intercept. Now, the y-intercept is going to be where x is 0. So if I make x 0, this is what I have. I have 3 times -1 squared, which is 1. So 3 times 1 times a -1/2 is -3/2. That gives me the point x of 0 and a y of -3/2. So here we are, and I'm now ready to go ahead and graph. So we start here. I'm going to go through my -3 almost like a straight line. Make sure and pick up the y-intercept. We'll pick up this x-intercept, and remember we're bouncing off of it, and then end up over here. Now this is just a very rough sketch. The important parts is that you want to make sure that you're above the x-axis when you're supposed to be, below the x-axis when you're supposed to be, your end behavior is correct, your y-intercept is correct, your x-intercepts are correct, and the behavior around those x-intercepts is correct. We're not really sure from what we know in college algebra or a pre-calculus standpoint, we're not really sure how far down this goes. We would need to have a little bit of calculus to figure that part out. So we're happy at this point with this bit of a sketch of our polynomial. Now let's graph this polynomial function. Y equals x cubed minus 12x squared plus 44x minus 48. I do have my leading term at the ready. It's a positive coefficient and odd, which means I'm going to start down here and end up here. And I know that my my y-intercept is going to be 0, -48. I'm going to come down here and just label this a -48. We could make this a scale of -24 and -48, just 24 units for every grid line there. And now I need to know what my x-intercepts are, my zeros. So this is where our work comes in handy, that we've learned how to find zeros. Let's go ahead and start here. Let's say I have my polynomial in here. There aren't any missing terms. Be careful of that. I'm going to start with a possible rational 0 of 1. Let's see what happens. 1 times 1 is 1. Minus 12 is -11. -11 times 1 is -11. Plus 44 is 33. 33 times 1 is 33. Minus 48 is -15. That didn't work. So let's go ahead and try the next possible rational 0. I'm going to try 2. I carry down the 1. 1 times 2 is 2. 2 minus 12 is -10. -10 times 2 is -20. 44 minus 20 is 24. 24 times 2 is 48. -48 and 48 is 0. So we have found a 0. I now know that the polynomial will partially factor as x minus 2 times x squared minus 10x plus 24. And now that I have this down to a linear factor and a quadratic factor, I can try and just get this factored. I have an x and an x, a -4 and a -6 will give me my 24, and my negative 10x in the middle that I need. So I have zeros of 2, 4, and 6. I don't have a multiplicity for those zeros more than 1, so and as I go through them, it'll be almost like a straight line going through. So let's go ahead and sketch the graph that we have. I know that I'm starting down here in this quadrant. So I'm going to come down here. I'm going to go through negative 48. I'm going to go through 2, through 4, through 6, and end up in that quadrant. Make sure and put arrows on both of the ends of that graph, and this is a very rough sketch of that polynomial function. Finding a polynomial from its graph. Let's find a polynomial of least possible degree with this graph. I can see here I have zeros of negative 2, 1, and 3. And if we would zoom in on each of those, we're going through those zeros in more of a straight type of way. So I'll bet that those are linear factors, meaning the multiplicity is just 1. So for my 0 of negative 2, I get the factor x plus 2. For the 0 of 1, I get a factor of x minus 1. For the 0 of 3, I get a factor of x minus 3. I know I may have some kind of a multiplier out here that is a coefficient of that entire polynomial. We'll need to find out what that is. Whatever I do, I need to make sure that I'm going through the point 0, 12. So that means that I get a y of negative 12 when all of the x's are 0. That would make the first factor 2, the second factor would be negative 1, third factor would be negative 3. So I have negative 12 equals 2 times negative 1 times negative 3 is going to be a 6a. Dividing both sides by 6, a is negative 2. So my final polynomial, I'll keep it in factored form, is going to be y equals negative 2 times x plus 2 times x minus 1 times x minus 3. And just as a final confirmation, if I were to multiply this all out, the leading term would be a negative 2x cubed, and the end behavior does show an negative and odd type of a function. Let's find a polynomial of least possible degree with this graph. I can see that I have zeros of negative 1 and 1. So I'll have some coefficient of a in front. I have an x plus 1 factor from the negative 1, 0. And from the 0 of 1, I'll have a factor of x minus 1. Now, with this 0, we're going straight through like a line. So we can assume that the power of that 0, its multiplicity, is just 1. But this one is bouncing off. We know anything that is going to be an even multiplicity will bounce off that 0. But we want the least possible degree, so we'll stick with an even multiplicity of just 2. Again, I need to make sure that I'm going through this y-intercept of 0, negative 4. So let's see what we can do with that. Y would be negative 4 if x is 0. So that would make this a 1 squared. It'd make this a negative 1. So 1 squared is 1 times negative 1 is negative 1. So I have a negative 1a equals negative 4. Dividing both sides by negative 1, I get a equals 4. So y equals 4 times x plus 1 quantity squared times x minus 1. And again, just to double check, if I were to multiply this out, my leading term would be 4x cubed. So an odd multiplicity, positive coefficient, and indeed it does start down here and ends up here. The intermediate value theorem says that a function is going through these points that are shown, and if the function is continuous, its graph must cross the x-axis. So we have no breaks in our graph. We're somehow coming from this point to here. There is some place intermediate between those 2 points where we're crossing the x-axis, or where we have a 0. Formally stated here, the intermediate value theorem, which is the zeros interpretation here, let f be a polynomial function. The intermediate value theorem states that if f of a and f of b have opposite signs, then there exists at least one value c between a and b for which f of x equals 0. Let's use the intermediate value theorem to show that this polynomial function has a real 0 between -4 and -3. So we know that we can find f of a and f of b and the sign of those by doing synthetic division. Let's go ahead and run synthetic division here. I have 1, -4, -20, 32, 16, and I'm going to run -4 through my division. So 1, -4, -8, 32, 12, -48, -16, 64, and 80, and we see that we have a positive. Let's see for the next one, if I run -3 through the synthetic division process, what happens? -3, -7, 21, 1, -3, 29, -87, and -71. Our remainder here is negative. Now, by the intermediate value theorem, f of a and f of b have opposite signs. There exists at least one value c between a and b where we have a 0. So we just state that. By the intermediate value theorem, there exists a 0 between -4 and -3.